Okay, this is your last video of the semester, and it's chapter 17, and the topic is electrochemistry. And this is going to be a little bit longer video because I've got to review something in the beginning. And this material is coming from chapter 8, so you definitely need to review this. The question here is going to be, write a balanced equation showing the formation of rust from iron and oxygen. And we're going to be trying to identifying what's being oxidized, what's being reduced, and describe how the electrons are being transferred. So the one thing I will tell you right off the bat is that the product is going to be Fe2O3 because iron has different components and there's different iron oxides, but that is the major form in which rust is in. So you look at this description, it says iron and oxygen, so you should be able to say to yourself, okay, well, I need elemental iron, and I have to react it with oxygen in the air to give me Fe2O3. Now you have to, of course, you got to balance this. And right off the bat, you might say to yourself, okay, I need a 2 over here for the 2 irons, and then you get to the oxygen, you realize, okay, well, that's not going to easily balance. There's 3 here, 2 there. Easiest way to balance that, put a 2 out in front here to give you 6 oxygens, then put a 3 out in front of here, you got 6 oxygens. With that, now you realize this 2 is no longer going to be working, and you actually need a 4 out there. Now that is balanced. Now let's take a look at what's happening here. This is an oxidation reduction reaction. Okay, so electrons are being transferred. And what you have to do is you have to figure out the oxidation states of all of the elements here to figure out what's happening with the electrons. This one's fairly easy, but we got to remember some rules. And one of the rules we learn, and you go back in chapter 8 and look at this, is that oxygen, for the most part, is -2. Okay? It can be other than -2 and in peroxides, but this is not a peroxide, so for the most part, oxygen is going to be -2. So when you're looking at this, you say to yourself, okay, oxygen over here is, because we're trying to figure out what iron is. That's what we don't know. Oxygen's -2, and there's 3 of them. So effectively, it's -6 here, which means each oxygen, what we're saying is each oxygen is -2. So we've got a total of -6 there. That means that iron must be +3 because there's 2 of those. Okay, don't worry about the 2 out in front of there because that's multiplied by the, don't worry about this 2, it's multiplied by everything. All you're looking at is the compound, Fe2O3. So iron must be +3 because that gives us a +6 to balance the -6. So now we know that we have what? 12 electrons being transferred here total. What we have is iron going from 0. Anything in its elemental state is 0. So solid iron is 0, and O2 gas will be 0. This oxygen down here of being -2 is in a compound. Just think about it. The periodic table, equal numbers of protons and electrons. Anything in its elemental state must be 0. That means that each iron is going from 0 to +3, and there's total of 4 iron. So we have, obviously we're losing, if you will, 12 electrons total. 3 for each iron and 4 irons. That means there must be 12 electrons being picked up somewhere. Well, we're going from 0 to -2, and there's 6 oxygen. So that's plus 12 electrons. That's balanced, and you see the electrons have to be balanced. So this is assigning oxidation numbers to be able to account for how many electrons are being transferred. It also tells us what's being oxidized and what's being reduced. And if you remember, if you go back and look at the definition of these, oxidation is the loss of electrons. And reduction, and that's the definition that works in all cases, gain of electrons. In this case, iron is being oxidized because it's losing electrons. It's going from 0 to +3. And what's being oxidized and reduced is going to be on the left side of the equation, nothing on the right side, because this is what's happening to the stuff on the left. And it'll be O2. That's gaining electrons. Now, what is the oxidizing agent? Well, the oxidizing agent is what carries out the oxidation. and therefore in itself is being reduced, and that will be oxygen. It's carrying out the oxidation of iron, and in the process being reduced. That confuses people, but the word agent tells you what it does. It's carrying that out. So the reducing agent then is going to be obviously be the iron, because it's being oxidized. And that's what you have to review and get comfortable with, or you really can't do much with electrochemistry. Here are your learning goals. There's several things here to look at. And this is included in your slide set, so please look these over and make sure at the end of the chapter you're comfortable with this. This is what we'll cover in this chapter. At the very end, we'll do stuff on fuel cells and batteries, but we don't have a lot of time to spend on that. And this is basic introduction to electrochemistry. What is electrochemistry? Well, basically the branch of chemistry that examines the transformation between chemical and electrical energy. And it's those redox reactions there. They are in section 8.6 that you'll need to review. Okay, let's look at running on electricity here now. So what we're going to do now, in this case, we just have a piece of iron and it's dumped in a bath of copper ions. And that has to be some sort of copper compound, obviously. It's probably copper sulfate based on the color. But the sulfate ion spectator, we don't really care about that. It could have been copper chloride. So what we're seeing here is the copper right here is being oxidized, losing electrons. Okay, and so that means, I'm sorry, I'm saying copper, the zinc. The zinc is this metal right here, right? So it's going to basically be coming off in solution. And the copper ions that are in solution already, see, this is the zinc right here. The copper ions that are in solution here, they're going to be plating out on the surface of the zinc, and that's going to give it actually a different color. And you can see it's almost like a black color there. So this is an oxidation reduction reaction. Of course, we balance electrons. There's 2 electrons in each case. They're being given up in a transfer. There's no balancing necessary here. In some cases, your half reactions have to be balanced. Okay, so that is basically what's happening. Appendix 6 actually has reduction and oxidation, reduction half reactions for you to look at and to use for answering some of your questions. So what we're going to do now is we're going to design a cell. So in this case, the electrons could migrate directly from the zinc to the copper because they're in the same system, in the same cell. But now what we do is we're going to separate them. And therefore the electrons are going to be forced to move through an external source. So that's what our electrochemical cell is. We're going to get it to basically do work. And the convention here is anode is where oxidation takes place, and cathode is where reduction takes place. That's the convention. That's always the case, no matter what cells we're talking about. So here's an electrochemical cell here. Now we've separated, it's the same one as before, but now we've separated, we've added another electrode. And what we have here is zinc once again being oxidized here, but the only way for the electrons to get to the copper for it to plate out is to travel up and over like this, and we're going to use that to force it to power a light bulb. The only thing we'll need to do is we'll have to have this bathed in a salt solution, and the ions there are going to be important because they can migrate back and forth to maintain an electrochemical balance. Because on the left you're generating zinc cations, and on the right you're consuming copper cations. So that salt will allow a balance to be maintained. Okay, so cathode is positively charged in this case, and the anode is negatively charged. And you see that basically the same type of thing that we saw right here, only we're forcing the system to power, in this case, a light bulb. The other thing that you need to get comfortable with is electrochemical cell diagrams. So what we're going to do is take that previous cell and we're going to write it in a notation that explains to us how the cell is constructed. So what we're going to do is we're going to say zinc solid was converted to zinc 2+ ions, and then copper 2+ ions were converted to copper solid. So the oxidation is always on the left, Okay, and you write it exactly the way it's occurring, zinc going to zinc 2 plus. This right here is your salt bridge, so effectively that is your phase, your bridge, sorry. And these here are phase boundaries. This one and this one are phase boundaries. And on the right, you have your written as your reduction, just as the reduction occurs, copper going to copper ion. So that's a cell notation. You need to be able to write one given the information, or you need to be able to tell me what's happening in the cell given an actual cell diagram. Now, the next important topic that's covered in your book is these standard potentials. Okay? Standard reduction potential, as always, we're going to standardize things and we're going to say, okay, 25 degrees C, basically, and everything is going to be in its standard state. So these are going to be written as reduction potentials, okay? And then we're going to have a standard cell potential. And this is a measure of the voltage. It's a measure of the EMF, which the EMF is just your voltage. And that's for the whole cell that we built. So for this previous one here, this has a particular voltage associated with it based on the differential preference for electrons between these two species. And that's the energy or the amount of work that you can do. So these standard potentials are going to be very important. So the cell we've been looking at, these cells we've been looking at, this zinc copper one we just looked at here, this is known as a voltaic or galvanic cell. They mean it is the same thing, just two words meaning the same thing. It's an electrochemical cell in which the chemical reaction is providing energy and work and capable of doing work. Okay? The cells we'll talk about at the end of the chapter are electrolytic cells. They're all electrochemical cells, but it's an electrolytic cell, not a voltaic or galvanic. That type of cell requires electricity to get the reaction to go. So it's basically a non-spontaneous system, where this is much more spontaneous. So this EMF of the cell can be measured. And it's measured by this equation. And if you use this equation, you won't run into any problems. The E naught of the cell is equal to the E naught of the cathode minus the E naught of the anode. Or if you will, since we know reduction occurs at the cathode, some people like to put E naught of the reduction minus E naught of the oxidation. Keep in mind that these are E's, so they are reduction potentials, written as reduction potentials, and I'll explain this further as we go forward. That's what this tabulated is in your book and in your chapter and in the appendix. They are reduction potentials. Okay, so here's some standard reduction potentials right here. Okay, now you see they're written as reductions. Copper plus 2 electrons, zinc plus 2 electrons. And this is the standard potential that's associated with that. I'll explain to you in a bit how that comes about. Your book covers this a little bit later. Kind of feel like it's a little bit out of order. But nonetheless, what we're looking at here is a cell. And if you take these reduction potentials and simply put them in the cathode, that's the reduction. We said copper's being reduced, so we're going to put that one in there. And then this one in here. Don't change signs or anything. Just use the equation. And it gives you the voltage, okay, for this particular cell. It's important to realize is that for these voltaic cells, the more positive E naught runs as the reduction. Okay? The other one has to proceed as an oxidation. That's what we said here. So effectively, the negative here is flipping this. and telling you, okay, it's not proceeding as a reduction, it's the reverse reaction, and therefore this has to be positive. That's why we have this equation with the negative sign here, because you literally are flipping the reaction. And we just said that, right? Zinc is not being reduced, right? It's being oxidized. And this is a reduction potential. So only one of them can proceed as a reduction, the more positive one, which means that one is more favorable to proceed as the reduction. The other one has to proceed as an oxidation. This is a really, really important concept, and you need to read and get comfortable with this. A couple other things about standard potential. It's an intensive property. It doesn't change. This is E naught specifically. Doesn't change with quantities. Now we will see that E of the cell will change with quantities when you get to the Nernst equation. So E naught is a measure, basically, you could think of that as the potential energy. Think about water flowing. Measure from the top of the waterfall to the bottom of the waterfall. Okay? That's what you're measuring, that difference. It doesn't matter how much water is flowing. The water does impact the amount of work you can do, just like the amount of zinc inside the battery will impact that. Okay? But the potential energy is the same. It's the difference between those two species that are in your electrochemical cell. This is an equation now, an important one that relates delta G. And through our discussion of spontaneity that I've mentioned a couple times, you might have started to realize there's going to be a connection here. So this equation allows you to relate the E of the cell, not the standard E, but the E of the cell. We'll get to the equation that shows you E of the cell and E naught together in a second here. F is the Faraday constant. You'll be given that as a constant. N is the same as always. Moles of electrons, though, in this case. C is charge, a measure of coulombs. Physics unit for that is coulombs. And if you will, this comes in handy. Volts are equal to joules per coulomb. So this is 9.65 times 10 to the fourth coulombs per mole of electrons. All right, so here's how we're going to define our standard potentials. We have to create this reference point. So hydrogen was chosen. This is a little bit tricky, but hydrogen with a platinum electrode, okay? And this is the reaction. Hydrogen being reduced because it's a reduction. We're going to give this going to say that half reaction has a voltage of 0. Now remember, no half reaction actually has a voltage. So when we're talking about these voltages here, half reactions don't make sense to have voltages, right? You only get a voltage when the circuit is complete. So that's the whole idea. Those voltages are a result of pairing it with the standard hydrogen electrode. That's what this gives you. So this is the reduction reaction. Now what we're saying here, these numbers, this 0.762 and this 0.342 that we saw over here, came from pairing it with a hydrogen electrode. And that's what you're seeing here. In this case, you get a positive value in both cases. So in this case, no, actually you get the negative value. You see the difference here. The negative E of the zinc is going to be positive. So E of the zinc is going to be actually negative here. And the E of the copper is going to be positive. Let's just jump to this and show you because it's getting confusing. Sorry about that. So here, right here, is the standard electrode. Where is it? 0. Okay. Now I've already highlighted copper and zinc. We've got them here and here. The zinc is negative because it has a lower reduction potential than hydrogen, but the copper is positive. So when you solve this for each of these, obviously this comes out to be negative and this is positive. So all these half reactions have to be paired with something to get a voltage, and that's what we're doing. We're pairing them with hydrogen. So this is our standard electrode. And when you look at this in class, we're going to spend some time on this and really talk about what is what are the best oxidizing reducing agents on this chart. Now here's the Nernst equation, and this is what I wanted to get to. This is effective concentration on E of the cell. So what we have here is an equation that relates. Oh, here it is here. First I want to talk about this. So, okay, reactions stop when one of the reactants is completely consumed. A commercial battery stops operating at its rated cell potential before its reactants are completely consumed. And that's just the nature of the battery. So the cell potential of voltaic cells is determined by the concentrations of reactants and products. So this, whoops. This depends on concentrations. And let's take a look at the Nernst equation to see that. So we have the E of the cell is equal to the standard E naught of the cell minus RT ln natural log of Q over NF. Look a little familiar? Delta G equals delta G naught plus RT ln of K. RT ln of Q, right? So at 25 degrees C, if we put in the Faraday constant, we can get N put in R, you wind up with E of the cell is equal to E naught of the cell minus 0.0592 over N log of Q. So this is just putting in the Faraday constant, putting in 25 degrees C, and putting in R. That's all that does is simplify that. So we can use the Nernst equation to predict how the potential of a voltaic cell changes as the cell reaction proceeds and the concentrations of products and reactants change. So this is analogous to delta G. E of the cell is like delta G, and E naught of the cell is like delta G naught. Delta G naught does not change. It is a measure of the difference between the reactants and products, just like E naught is. It's an intensive property, but E changes as delta G changes. That's almost like that instantaneous energy you have as a result of those changes in concentration. The last thing in the chapter is electrolytic cells, and we're not going to spend a lot of time on this either here or in the classroom, but what I want to say here is that electrolysis is basically energy used to drive non-spontaneous oxidation reduction reactions. So now you're actually going to be putting electrons in and forcing it to go in a non-spontaneous way. And here is an example of the two cells shown side by side. The voltaic galvanic cell on the left, the electrolytic cell on the right. You'll notice oxidation still at the anode. Everything else the same. The cations still move towards the cations and anions are still moving back and forth. The only difference here is that the anode is positively charged here and negatively charged here. So we'll spend some time on that in class, and that for now concludes the video.